Nothing beats. In this video, we are going to connect the ideas of continuity and differentiability, see how they are linked together, and what one idea implies about the other. So, it's time. Let's go. All right. Like I said, the goal is to find the connection between continuity and differentiability for a function, if that even is a thing. So let's try to figure this out. All right, so what we're going to do is look at a variety of graphs here to begin with and try to connect the ideas. The goal for each of these graphs is to first figure out the intervals for which the function, in this case y is equal to p of x, is continuous, and then also the interval for which the function is differentiable. And as we go through several of these graphs, we'll start trying to get an idea of perhaps how these two concepts are related to each other. So here's the first graph of p of x here. As we can see, it's a piecewise defined function, kind of this interesting looking graph as we see in blue. So first things first, part A here, let's figure out the intervals for which this function p is continuous. And as we can see, to the left of 2, all over here, the function is nice and continuous, but it is not continuous to the left of 2 because of that hole right there. So hence we could write negative infinity to 2. This function is continuous. And then notice right here to the right of 2, the function is also continuous, and actually it is continuous from the right at 2 because of that dot right there. So we can list the next interval as 2 to infinity, including the 2. So what about differentiability? Well, this function to the left of 2, nice and smooth. Everything is looking nice and differentiable. And everything to the right of 2, also nice and smooth, differentiable. But at 2, there's that problem spot, right? There's that jump, as we see in the graph. And so we're not going to be able to draw a tangent line at 2 that is unique. And in fact, remember from the last video, functions are not going to be differentiable at endpoints. So for part B, where are we differentiable? Well, we're differentiable everywhere except at 2. So hence the open interval, negative infinity to 2, union with 2 to infinity. Notice I didn't write the union for the continuity intervals in part A, because if I union that open interval with the closed interval on this one right here, then it would end up implying that we include the 2. So we just list them. So in this case, the function is not continuous at 2. And it's also not differentiable at 2. Let's look at another one. In this graph, we are given the graph of y is equal to k of x. Right here, as we can see, kind of looks like an absolute value function. And again, we want to figure out where this function is continuous and also differentiable. As we can see in the graph, there's no holes, there's no jumps, there's no funky stuff going on in that sense, and thus this function is continuous for all real numbers. So let's just write it right here, part A. This function is continuous from negative infinity to infinity. All real numbers is continuous. However, in part B, where is this function differentiable? As we discussed in the previous video, we see that corner right here at x is equal to 1. And we know at these corner locations, the function is not differentiable because the slopes of the corresponding lines to the left and to the right of this location, those slopes don't match up. And thus, this function is differentiable from negative infinity to 1. Not at 1, jump over that, and then from 1 to infinity. So we can see in this example, the function is continuous everywhere, but there's actually this location at x is 1 for which the function is not differentiable. So we should be kind of thinking about what that's telling us here as we move forward. Let's look at another one. Here's a function f of x. Okay, kind of looks like a polynomial function. And in this graph, we see it's nice and smooth everywhere. No holes, no jumps. Doesn't seem like any funky stuff is going on here. And for that reason, in part A, where is the function continuous? Well, again, it's going to be continuous for all real numbers x, from negative infinity to infinity. And where is this function differentiable? Well, it seems like there's no problem spots. There's no cusps. There's no corners. There's no vertical tangents. There's no discontinuities. So it seems to be that this function is differentiable also for all real numbers. So what are we trying to get at here? A couple of questions. First question, is it possible for a function, say f of x, to be continuous at a location, let's say x is a, and for f prime of a to be undefined? And the answer to that is yes. As we saw in this one right here, right, that function was continuous at x is 1, but it was not differentiable there. And according to the previous video we also looked at, there's a variety of other ways for which that can happen. So, you know, think corners, right, cusps, vertical tangents, and even discontinuities. So there's a variety of ways that can happen. So the first thing you want to be thinking right now is, just because a function is continuous at a location doesn't tell us whether or not the function is going to be differentiable at that location. But here's a second question. Is it possible for a function f of x to be differentiable at a location now, x is a, but to be discontinuous at that same location? And the answer to this is no. As we saw in the first example moments ago, the graph that looked kind of like this, if you recall, right? That function was not continuous at this location. Let's just call that location of discontinuity, say it's A. And because of that reason, it was not differentiable, but it was originally not continuous, right? We said it's not continuous there, and then it ended up not being differentiable. Now, if a function is differentiable at a location, then its derivative, of course, exists at that location. And so you try to think, how can the slope be defined at a particular location in the graph of the function, but the function is not continuous at that location? And of course, there's a variety of ways we can be discontinuous at a location. It could just be that the limit doesn't exist, like in this picture that we see on the screen. It could be that the limit is not equal to the value of the function, or the function may just be undefined entirely, right? In all three of those cases, if we are discontinuous, there's no way for the function to actually have a defined slope at that location. So then, what we're going to get into here is this theorem that we're trying to hint at, is that differentiability implies continuity. In other words, if you are differentiable at a location, then you must also be continuous at that same location. And more specifically, let's say that a function is differentiable at the location of x is equal to a, then it must also be continuous at the location x is equal to a. Now, we're not proving this, but we're trying to get a sense of why that's true in this video, right? So that statement's important, right? Differentiability implies continuity, but there's another way to write this in an equivalent form, but slightly different. And that's why I want to bring up this idea of what's called a contrapositive right here of an if-then statement. Now, this is not a logic and analysis class, but we can talk about this right now in this video because it is relevant and it's important to rewrite a statement in a different form with equivalent truth values. You want to learn more about logical equivalencies and whatnot, go to my playlist, Logic and Analysis, in my Math and Beats playlists. Excuse me. So what is a contrapositive? Let's suppose you have two statements. let's call them P and Q. So a statement is just some sentence that is either true or false, right? 2 plus 2 is 4. That's a statement. 5 minus 3 is 18. That's a statement because false. So it could be true or false. Suppose you just have two statements. It could be anything as long as there's a truth value associated with it. Then you consider what's called the compound statement. If P, then Q. So if one statement, then another statement. And we write this with a P and an arrow, then Q. So if P, then Q is how we say that. Kind of like we had in the theorem above. Now the contrapositive of the statement if P, then Q is written like this right here, and that is pronounced if not Q, then not P. So that's always what's called the contrapositive of the original statement. You negate the Q, and that becomes your if part, if not Q, and then you also negate the P. You say if not Q, then not P. That is how we write a contrapositive. And it ends up, and this could be proven through logic tables, that a statement, if P then Q, and its corresponding contrapositive, if not Q, then not P, those two statements always have the same truth value. Meaning that if the first statement is true, then the second statement is also true. That is, like, pretend if P, then Q. If that's true, then if not Q, then not P, that also must be true. And if P, then Q, if that's false, then it's contrapositive. If not Q, then not P also has to be false. So they always carry the same truth values associated with them. And again, I'm not proving that here, but it can be proven again through using logical tables. So the whole point of talking about the contrapositive of an if-then statement and how it relates to what we're talking about is because we have this theorem that we had stated. If a function f of x is differentiable, so here's your P statement, right? If that part, then here's my Q statement, right? F of x is continuous at x is a. So if a function is differentiable at x is a, then the function is continuous at x is a. But now we know that the contrapositive of a statement always has the exact same truth value. And of course, this is a theorem, so it's true. So if I rewrite that in a contrapositive form, then we can write this right here. If a function is not continuous or discontinuous at x is a, then f is not differentiable at x is equal to a. So you notice that this right here is now not P, and this is not Q. That's our contrapositive. It means the exact same thing. So these two statements are exactly the same thing, just written in different forms, right? And sometimes it's more useful to use the second one, and that is if a function is discontinuous at a location, then the function cannot be differentiable at that location. But equivalently, if a function is differentiable at a location, then the function has to also be continuous at that location. And that's really the big takeaway from this video, is this connection between differentiability and continuity. Differentiability implies continuity, but of course, as we've seen in the video, continuity does not necessarily imply differentiability. All right, what we're going to do now is look at one last example utilizing the theorem that we just came up with. And what we're going to do is look at this graph of this function here, y is f of x, that's on our screen, this piecewise defined function, and we're going to ask some questions like, where is it continuous, where is it differentiable, that kind of stuff. So indeed, that's the first question. Notice the function we're only considering on the closed interval from 0 to 8 here, and the first part is, can we figure out all the values of x for which this function is continuous? So notice that we have a problem spot right there at 4. We also don't have a value defined at 6, and then we have one-sided continuity at a variety of locations. So what we'll do first is we'll list the intervals of continuity, and then we'll also just state the locations for which the function is not continuous, okay? So as we start at 0 and we move along, we can see that we are continuous from the right at 0. And as we move from the left to the right towards 4, we see that there's that hole right there, so we are not continuous from the left at 4. So the first interval of continuity would be from 0 closed to 4 open. And then we definitely can see we're not continuous at 4 overall, but just considering the intervals of continuity, right here we can see we are continuous from the right at 4. And as we move along, we get to the problem spot of 6. We are not continuous from the left at 6 since the value doesn't even exist there. So the next interval would be closed at 4 and then all the way up to 6 open. And then finally, as we move from 6 to 8, we can see again we are not continuous from the right at 6. And as we get close to 8, the value of the function is equal to the limit from the left, and hence we are continuous from the left at 8. So the last interval would be 6 open to 8 closed. So those are the intervals of continuity, but we should just take note that overall, if we don't consider the one-sided continuity, that this function f is discontinuous at x is equal to 4 and x is equal to 6 overall, right? We're not continuous there. At 4, we're not continuous because the limit doesn't exist, and at 6, we're not continuous because the function is undefined there. So from the previous results that we talked about in this video, we can instantly say that at x is equal to 4 and at x is equal to 6, the function will not be differentiable because it is not continuous there. If we are discontinuous at a location, we cannot be differentiable either. And so that's the second question here, part B, on this same interval 0 to 8, determine all values of x for which the function is differentiable. So we know we're not going to be differentiable at 4 and 6. But because we're only considering a closed interval here, and we know that functions are not differentiable at endpoints, we know we're not going to be differentiable at 0 and also at 8. And then finally, we have another corner right there, right, at x is equal to 2. So at that location, we're also not differentiable, even though the function is continuous at the location x is 2. So let's list those out. All right, we're not continuous at 0 because it's an endpoint. And then, so we put a little open right there at 0, right? And then we get to 2, right? We're differentiable, we're not differentiable at x is equal to 2. So 0 to 2, open. Union, all right, 2, we're not differentiable. And then we move along from 2 to 4. We are discontinuous at x is equal to 4. So we're not continuous at 4. And then jump over that 4. Keep moving along. Differentiable, differentiable, differentiable. Not differentiable at 6 because we are not continuous at x is 6. So 4 to 6. Jump over 6. And then as we move from 6 to 8, we're nice and differentiable, but 8 is an endpoint, so we're not differentiable there. So 6 to 8. So there is our intervals of differentiability. At 4 and 6, there's discontinuity, so we're not differentiable. At 0 and 8, they're endpoints, so we're not differentiable. And then at x is equal to 2, there's that corner, so we're also not differentiable there. Otherwise, all the other locations in this interval, we are differentiable. And then finally, we're asked to draw the graph of y is equal to f prime in the plane above. So this is kind of like that problem that we looked at in a previous video, in which we see that the different pieces of the graph are linear. So we know that lines have constant slopes. So if we want to draw the graph of f prime here, then of course we are going to just look at the slopes of each of these lines. So let's look at each line. Let's call the first segment y1, the second one y2, the third one y3, and the fourth one y4. All right, and then we got to just find the slopes. So for the first part, y1, that's defined between 0 and 2. So if I go over 2 units, then what's going on with the slope? We see that the slope is going to be over 2, up 2, so the slope is 1. So here, slope, call it m1, is 1. What about the next piece from 2 to 4? Well, again, we draw a little triangle to help us visualize here. Notice that we are going down from 4 to 1, so that's down 3, and over 2. So slope of this second line going to be a negative 3 over 2. And then y3, we're going from 4 to 6 in the x direction, down from 2 to 1, and then over 2. So that slope, call it m3, is going to be a negative 1/2. And then finally the last piece from 6 to 8. Notice we're going over 2 units and we're going up 1 unit. So the slope of this last piece, call it m4, is a positive 1/2. Okay. So now we can draw the graph. Let's draw it maybe in the color of red. All right, from 0 to 2, my slope is 1. We're not differentiable at 0. We're not differentiable at 2 because endpoint at 0 and corner at 2. So that graph is just going to be a hole at 1. Slope is constant of 1 all the way to 2, and we get a graph that looks like that. Now the plane is a little bit not big enough to draw it, but let's just kind of extend it down here, if you will. And let's just suppose that negative 3/2 is right there, okay? It's not particularly exact to scale, but just get the idea because the next slope is a negative 3/2 from 2 to 4. So I'll draw in my constant slope of negative 3/2 from 2 to 4. And then for the graph of y3 there, from 4 to 6, my slope is a negative 1/2. So perhaps negative 1/2 is about right there. There's a negative 1/2. And I'll draw my constant slope of negative 1/2 from 4 to 6. And then finally, from 6 to 8, the slope is a 1/2. 1/2 on the graph here is approximately right there. And so then I'll draw my last piece of the puzzle from 0 to 8, like so. And that red graph is the graph, of course, of the derivative of this function, f prime of x. So all consistent with each other. So in this particular example, we had 2 discontinuities. We weren't differentiable. We had 2 endpoints. We weren't differentiable. And then at x is 2 was a corner, and even though the function was continuous there, it was not differentiable. Hence the holes in the graph of f prime of x. So there you have it. That's the end of this video. And after this video, we're going to start diving into all the differentiability rules, starting to actually find all these different derivative functions for all the different functions that we can imagine in single variable world. So until next time, it's Math and Beats, and I'm out.